Okay, in this example, we're told we have air entering a compressor of a cold air standard Brayton cycle. So we're going to do a cold air standard analysis here. And the Brayton cycle has regeneration and reheat. We're told the conditions coming into the compressor. We're told the compressor ratio and the inlet temperature for each turbine stage is 1400 Kelvin. We're also told the pressure ratios across each turbine stage are equal. So we have, there are actually two turbine stages here. I don't think that's mentioned in the problem statement, but I'm just telling you it here. The turbine stages and compressor each have isentropic efficiencies of 80%, and the regenerator has an effectiveness of 80%. Calculate the thermal efficiency of the cycle, the back work ratio, and the net power developed by the cycle. So the first thing we're going to do is just sketch out the cycle. There's a lot going on here, so it'll take just a moment to sketch it all out. We have the compressor that's connected via a shaft to the first stage turbine, we'll call it T1, and then there's a second stage turbine, T2. And then we have our net power coming out. Coming out of the compressor, we go through a regenerator. So this is our regenerator. And that leads into the combustor, where some heat is put in. And then out of the combustor, we go into our first stage turbine. Out of that, we go through the reheat, so there's actually a secondary combustor. So this is our first combustor up here, and then this will be our second combustor here. So there's some additional heat. This is our reheat part. We'll call it Q dot N2, and this will be Q dot N1 up there. And then out of that combustor, we go into our second stage turbine. Out of our second stage turbine through the regenerator. Out of that regenerator down into a heat exchanger where we dissipate heat to the surroundings. And then out of that heat exchanger back into the compressor. So a lot of components in here. So let's put some numbers associated with each of the states. So state 1 leads into the compressor, state 2 goes into the regenerator, X goes from the regenerator into the first combustor. Out of the combustor we have state 3 going into the first stage turbine, state 4 goes into the reheat combustor, state 5 comes out of that into the second stage turbine, state 6 goes into the regenerator, and state Y goes from the regenerator into the heat exchanger, and then we're back to state 1 again. Okay, so kind of a complicated looking example, but we're going to analyze it basically the same way we've analyzed every other cycle in this whole class. All right, so we're doing a cold air standard analysis, so let me just put some quantities associated with that. We're going to use the gas constant for air, that's 0.287 kilojoules per kilogram Kelvin. And we're going to also make use of the specific heat ratio at constant pressure. So I'm going to look that up. And from a table, that's 1.005 kilojoules per kilogram Kelvin. And I looked it up specifically at 300 Kelvin. The reason I did that was because that's the inlet temperature, is 300 Kelvin. So it's at state 1. We're just assuming that it's constant. The cold air standard analysis is not particularly accurate here because you'll notice that the temperature coming in is at 300 Kelvin, but the maximum temperature is 1400 Kelvin. So it's a pretty large temperature range. Over that wide of a range of temperatures, the specific heat ratio at constant pressure for air would change quite a bit. So this is not a particularly accurate analysis, but we're asked to do it in the problem statement, so we'll do it nevertheless. All right, so to find the net power, I'm going to start at part C here, find the net power developed by the cycle. To do that, I'm going to apply the first law to a control volume that surrounds the compressor and turbine stages. Okay, so if I do that, so first law to compressor and turbines, and I'm going to assume that it's steady state, steady flow, adiabatic, and neglect changes in kinetic and potential energy when I write out the first law. So when I go through all that, simplify it down, you'll get the net work out, or the net power out, is the mass flow rate times H1 minus H2, that's the compressor component right over here, plus H3 minus H4, that's the first stage turbine. And then for the last stage turbine, it'll be H5 minus H6. Okay. Since we're doing a cold air standard analysis, just keep in mind that for a cold air standard analysis, we assume that we're dealing with a perfect gas, meaning the specific heats are constant. So that means that delta H would be like Cp delta T. So I can rewrite that net power out in terms of temperatures. So this will be m dot Cp T1 minus T2 plus T3 minus T4 plus T5 minus T6. So really I don't need to find specific enthalpies, but instead I'll just find the temperatures. All right, so that's how, so I'll need to find all those temperatures to find the net power out. Now to find the back work ratio, let me just go for the definition of that. So the back work ratio is defined as the power into the compressor divided by the power coming out of the turbines, right? So that will be just the power in. We can find that using the first law applied to the compressor. So let me draw that out here. So if we draw a control volume around the compressor and apply the first law there, so first law on compressor, again assuming steady state, steady flow, adiabatic, negligible kinetic and potential energy changes. What you'd get is the W dot in to the compressor will be m dot H2 minus H1. Or, since we're doing a cold air standard analysis, it'll be m dot Cp T2 minus T1. So that's how we'll find the power going into the compressor. To find the power coming out of the turbine, I can just make use of the net power out and the power into the compressor. So W dot out net, or I'm sorry, out of the turbines will be the net power out, and then add back in the compressor power. So that's how we will find that one. So the back work ratio will just be W dot in all over W dot out net plus W dot in from the compressor. Okay? Because the reason I did that is because the net power out already takes into account the power that is having to go into the compressor. So I'm just eliminating that part of it. Okay, you can see that if you look at this expression right here, the net power out, here's the contribution from the compressor, the part that we have to put energy into, and if I add in this expression, you'll see that the H2 and the H1 will cancel out, and you'll be left with just the turbine components. So that's how we'll find the back work ratio. Then to find the thermal efficiency, we'll need to find the total heat going into our cycle. So we'll have some heat coming in through the first combustor, and then we'll have some heat coming in through the reheat combustor. So we'll need to apply the first law to both of those. So let me sketch that out. So we'll have a control volume around the first combustor, excuse me, and a control volume around the second combustor, and we'll apply the first law to both of those. So first law on combustor 1 and combustor 2. And again, we'll assume steady state, steady flow, negligible kinetic energy and potential energy changes. And in this case, these are passive devices. They're not adiabatic because we're adding heat. They're just passive devices. So Q dot in from the first combustor will be m dot, let's go back up, should be H3 minus Hx. And the Q dot in from the second combustor will be m dot, and if I look up here, it should be H5 minus H4. And since we're dealing with a cold air standard analysis, I can write this as Cp delta T. So this would be T3 minus Tx, and the bottom one will be Cp times T5 minus T4. And then if I want the total Q dot in, it'll be adding the two different Q dot ins together. And then to find the thermal efficiency of the whole cycle, it'll be the net power out, all divided by the Q dot in, where the Q dot in is this Q dot in here. It's the total heat that we're putting in. Okay, so now we know how to calculate all the various quantities that we want. The only issue is we need to find the temperatures at all of these various states. You can see the temperature shows up in so many of these things. So we have to find the temperature at the various states. So let's do that next. So we'll start at state 1. So at state 1, we're actually given much of the information there. If you go back up to the problem statement, we're told the pressure and the temperature. We're also told the mass flow rate. So let's see, the pressure ratio, or the pressure was 100 kilopascals, temperature was 300 Kelvin. So P1, 100 kilopascals. Absolute. T1 was 300 Kelvin. And we're also told the mass flow rate was 6 kilograms per second. Okay, so we know T1. Let's go to state 2. For state 2, we're crossing the turbine, and we're told that the turbine, we're crossing the compressor, I apologize for that. And we're told the compressor has an isentropic efficiency of 80%. So we're going to make use of that isentropic efficiency to find the conditions at state 2. Okay. So let's use that isentropic efficiency for the compressor. That's defined as the power into the compressor if it was isentropic, divided by just the power in under actual conditions. And if you use the first law applied to that compressor, the numerator would be H2S minus H1. Denominator would be H2 minus H1. Since we're dealing with a cold air standard analysis, so it's a perfect gas, this will be T2S minus T1 times Cp on the numerator. The denominator would be Cp T2 minus T1. And then we can rearrange that to solve for T2. And this will look like the following. So there's our expression for T2. We know T1, we know the isentropic efficiency of the compressor, we just need to find T2S. So to find that, so let's call this state, erase that, state 2S. To do that, what we're going to do is make use of the fact that we're dealing with a perfect gas, so constant specific heats, and an isentropic process. And for that, we have some convenient ratios that we can work with that relate to temperature, like T2S over T1, to the pressure ratio, P2S over P1. In terms of the specific heat ratio K. I should have written this down up here, but when we were writing down the gas constant for air and the specific heat at constant pressure for air, let me put down the specific heat ratio for air. It's 1.4. Okay, so this expression, this temperature ratio in terms of the pressure ratio is only for a perfect gas undergoing an isentropic process. Now if it was an ideal gas where the specific heats could vary, then what we would use is the relative pressure ratio, just like in the first example I worked for this lecture. So the P2S over P1, we know that that's the same as P2 over P1 because we're going between the same pressures, and that was given as equaling 10 in the problem statement. So we can then solve for T2S. That comes out to be 579.21 Kelvin. And then we can then make use of our isentropic efficiency to solve for T2. That comes out to be 649.01 Kelvin. Okay, so now we have the temperature at 2. Let's go to the temperature at 3. Temperature at 3 is actually given. So temperature at 3 is coming out of the combustor. We're told the inlet temperature for each turbine stage is 1400 Kelvin. So state 3 leads right into the first turbine. We'll come back to state X in just a moment. Okay, we'll do that toward the very end when we analyze the regenerator. But for now we're told that T3 is 1400 Kelvin. And for that matter, T5 will also be 1400 Kelvin because it says the inlet temperature for each turbine stage. So T3 and T5 are the same temperatures. So let me make a note of that. T3 and T5 are 1400 Kelvin. Okay, so we know those temperatures now, so that's good. Let's move on to state 4. State 4 is right down stream of the first turbine stage. Right, so state 4 is right there. So we're going to make use of the isentropic efficiency for the turbine. Recall that the definition of that is the net, or the power that we get out of the actual turbine divided by the power that we get out if it was isentropic. So this will be H3 minus H4 all over H3 minus H4S. And since we're dealing with a perfect gas, it'll be Cp T3 minus T4 all over Cp T3 minus T4S. And if we do some rearranging there, we'll get T4 is T3 minus the turbine isentropic efficiency multiplied by T3 minus T4S. There we know T3 already. Oops. We know T3 already. We know the isentropic efficiency. We just need to find T4S. To find T4S, we'll make use of the fact that, again, it's a perfect gas. Let me try that over again. Perfect gas and an isentropic process to get to state 4S. So this is what I'm doing is state 4S here. So perfect gas and isentropic, so we know T4S over T3 will be P4S over P3 to the K minus 1 over K. Now, we know T3. What we don't have yet is P4S over P3. So let me go back up to the problem statement. Sorry, I'm having to go back and forth so much. But remember, we have two turbines here. So the temperature the pressure at 2 and the pressure at 3 will be the same, right? Because we're going through a regenerator, there's no pressure change. We're going through the combustor, no pressure change. So P2 and P3 are the same. Now, we also know that P6, when you go through the regenerator, its pressure doesn't change. When you go through that heat exchanger, the pressure doesn't change. And so then P6 will equal P1, right? So the ratio of P2 over P1 will equal P3 over P6. Okay. That doesn't tell us P3 over P4, or for that matter P5 over P6, but we can relate these together, right? So P3 over P6 is like P3 Let me erase that. Sometimes my brain gets ahead of my hand here. So P3 over P4 times P4 over P5 times P5 over P6. I'm just kind of chaining these together. So you can see the P4s cancel out and the P5s cancel out, and you're left with P3 over P6. And what I'm trying to find is P3 over P4. So P4 over P5, that one's going to equal 1 because that's just going through the combustor, and we know the pressure doesn't change there. So what we're left with is P3 over P6, which of course we said before was equal to P2 over P1. It's going to be P3 over P4 times P5 over P6. Okay? So as of right now, we don't know how much pressure, what the pressure drop is across T1 or the pressure drop across T5 is. We don't know. But if you go back to the problem statement, it says the pressure ratios across each turbine stage are equal. So that means that P3 over P4 is equal to P5 over P6. So this would be like P3 over P4 squared, right? Because these are equal. That's given in the problem statement. So then P3 over P4 will be the square root of P2 over P1. And that's also going to be equal to P5 over P6 because P3 over P4 and P5 over P6 are the same. All right, so this will be just equal to the square root of 10. All right, and I think that comes out to be 3.162. So that's the pressure ratio, P3 over P4 as well as P5 over P6. Okay? So we're going to make use of that down here. P4S over P3, we now know, we just figured it out, that's going to be 1 over 3.162. So that means we could solve for T4S. That comes out to be, let's see, did I calculate that one out? I don't know if I actually, yeah, I calculated that out. That's 1007.56 Kelvin. And then that gives us T4 from our isentropic efficiency expression. That comes up to be 1086.05 Kelvin. All right. Now state 5, we already figured out. That was 1400 Kelvin. That was given in the problem statement that the temperature leading into each turbine stage was 1400 Kelvin. So we have T5. And to find T6, it's going to be exactly the same process as what we just did for state 4. We still have an isentropic efficiency of the turbine of 80, or I'm sorry, it was 80%, I think, right? Yeah, we're told that both turbine stages have an isentropic efficiency of 80%. So we'll still have the same kind of expression here for the isentropic efficiency. T3 and T5 are the same. We have the same efficiencies. We have the same pressure ratio across the second stage turbine. So everything will be the same. So you'll find that T6S is also 1007.56 Kelvin, and T6 will be 1086.05 Kelvin. So it's all exactly the same. All right. So we have most of the temperatures we need. We still need, so if you go back up here, we've done temperatures 1 through 6. So you can see that that gives us everything we need to find the net power out. Also gives us what we need to find the power into the compressor, which means that we can find the back work ratio. The only thing we need still is Tx, because we need that to find the thermal efficiency, the heat transfer and then the thermal efficiency. So let's find Tx. So the way we'll find Tx is we'll draw a control volume around the regenerator. Well, actually, we don't even need to do that. What we'll do is we'll make use of the regenerator effectiveness. So we're told the regenerator effectiveness is 80%. Now, remember what the regenerator effectiveness is. It's basically how the specific enthalpy changes across. So it'd be like Hx minus H2 divided by H6 minus H2. The idea here is that for 100% effectiveness, the H6 and the H6 and the HX would be the same. So let me write this down. The regenerator effectiveness will be Hx minus H2, because that's the change in the specific enthalpy from the compressor to the combustor, divided by what we would hope would be ideal, would be H6 minus H2, because this is H6 was the temperature leading into the regenerator, right? This is kind of the hottest part leading into the regenerator, and ideally we would want what's going into the combustor to have the same specific enthalpy. Since we're dealing with a perfect gas, we can write this as Tx minus T2 times Cp, and similarly in the denominator. So we could rearrange this to solve for Tx. Right, so I think I did my algebra correctly there, and so we know all the values in that expression, so we can solve for Tx. It comes out to be 998.64 Kelvin. So now we have all of the temperatures that we need to do all our calculations. So if you substitute everything in and work it all out, the net power out is 1680 kilowatts. The power into the compressor comes out to be 2100 kilowatts. So the back work ratio, when you work that number out, comes out to be 0.556 or 55.6%. The total heat in, this is the total heat in, is 4300 kilowatts. And so the thermal efficiency of everything together, it comes out to be 39%. All right. And as a little bonus, we weren't asked to do this, but I'll sketch it out anyway. I'll plot the TS diagram for this cycle. So we're starting at state 1. I'll put it here. Here's the isobar corresponding to state 1. State 2 would be on this isobar. Would go vertically if it was, so state 1's there. Vertically would give us state 2s, but we have some isentropic efficiency of the compressor, so there's going to be a little bit larger entropy at state 2. Then we go through the regenerator to state X, and that's a constant pressure process, so we go there. Then we go through the combustor to state 3, that also is a constant pressure. So we'll go to there. There's our state 3. So all these pressures are the same. P2 equals Px equals P3. Here we have P1. Then from state 3 to state 4, we go through the first stage of the turbine, and we calculated the pressure ratio. The pressure ratio is the same across both turbines. So this will be P4 down here. So here's what it would look like if it was isentropic. So that would be 4s. But it's not isentropic, so we go to state 4 here. Then we go through the reheat combustor. That's a constant pressure process, and that gets us up to state 5. Now the temperature at state 5 and state 3 we were told were the same. Those were leading into the turbine. So state 5 will be right there. So we'll go through the reheat combustor upwards. So here's P5 is equal to P4. So now we're going to go through the second stage turbine. So that's what it would look like. Erase this. If it was isentropic, so this would be 6s, but of course it's not isentropic, so state 6 is right there. And then we go through the regenerator. So that'll take us to state Y. That's a constant pressure process. And then we go through the heat exchanger, the final heat exchanger, to close the loop. And that's a constant pressure process. So that isobar down here, this all has P1 equals Py equals P6. That's the lowest pressure. So that's what our cycle looks like when we have the reheat portion for the turbine stages. You can see what happens there is we go along the same isobar, but we increase the temperature. So we're going up like that. And then we have the regenerator, which all that does is just shifts us further along on the isobar to higher and higher temperatures here. All right, I think that's everything for this example. So we'll go ahead and end it there.